So I'd like to compute this, the variance. But let's stick to this case to make things simpler. You know, I don't, the variance of this time here, I have to work. It's the same as the variance there, so yeah, it's no big deal. What's the you tell me, what's the second moment? Well, not too hard, right? Because n times t is equal to k, right? And then I have 1 over square root of n. I square that, I get 1 over n. I should be able to do this in our sleep, right? And I look at the second moment of a sum of zero mean independent random variables. All the cross terms cancel. I just get 1 over n. This is going to be n times sigma squared. And I missed something. Not n, k. Because they're k terms, not n. Right? So I get k over n times sigma squared. And what's k over n? It looks like t. All right. Okay. So I have something where the variance is growing linearly with time, and the mean is 0. And so at least on a boundary interval, it's well behaved. Now, what does it converge to as n goes to infinity? It's limit theorem number 2. Remember, I listed my 3 favorite, or everyone's 3 favorite limit theorems. First was the law of large numbers. The third was the large deviation principle, and the second was the CLT. So what does WNT converge to? Well, we know it goes to a Gaussian. At least, I mean, if we take t equals kn, now as n goes to infinity, that's jittering around. So it's hard to, k would have to be a function of n. But, you know, there's some garbage terms we have to deal with. But this is going to converge it to a n0 t sigma squared random variable as n goes to infinity in distribution by the CLT. It looks a little different than CLT again because, you know, it's like you'd have to deal with a garbage term. The fact that you look at the floor here, you know, but basically you just throw away that little bit, it disappears. Okay. All right. But that's not very satisfying. I said that random processes are just function-valued random variables. I want the sequence of functions to converge in some sense, not this. This is boring. Yep.
So that limiting random variable, would that imply the second moment's not finite as t goes to infinity?
Why? No, we have, as t goes to infinity, sure. No.
Well, then it's not a member of L2.
Yeah, it is. No. For each random variable, we define L2 for random variables.
Yeah.
Yeah. Not random processes, random variables.
Yeah,
So for each t, it doesn't matter anyway, but it's not actually, that's really a side topic, but this is an L2 for each t and n. Okay? So we're not talking about uniformity and, yeah. Okay, so, so basically, in fact, you can prove the processes converges. And what do you think, you know, all right, in fact, so this is deep. This I claim, you know, you just think a little bit, it's not that far from the CLT. But the fact that this converges in distribution of stochastic process, first you have to think, what on earth does Professor Mine mean by that? How would you define convergence in distribution of stochastic processes? Think about a random vector, you know, like a bunch of, a random sequence of random vectors converging. You know, you would look at the joint CDF. Well, you do the same thing here. So this is the trick that you always do, is you make things finite dimensional. So you basically have a stochastic process here, but you define a random vector. So in this case, a capital n-dimensional random vector, and you look at the joint CDF for that random vector. All right, so that's what this is, right? I'm looking at the joint CDF for the random vector, which is the W evaluated at these time points. And so you want that to converge for every time points you choose and every constant C that you choose. So this is all finite, but it could be, n could be 10 to the 10 to the 10 to the 10 to the 10th, okay? So that's what you mean. And then you have to say, what the hell is W, you know? So you know it's got to be Gaussian for each t with this variance, and it has to be, I mean, with mean 0 and variance t sigma squared. But it has some amazing properties. And then we're going to close, I suppose. W is Brownian motion. Okay, which I can now define, sort of, because you'll never, I mean, well, let's write down some properties. What is W0? Anybody can see it? Just look over there. Look over here. And for every single n, it's 0, so it's going to be 0 in the limit. B1 is the fact that it's still a random walk, but in continuous time. Tn. So you really, again, inheriting a property of the random walk. So if you looked at a discrete time equivalent, this would have independent increments. Okay, but these delta k's can have an arbitrary distribution the second moment. Well, now we have another property. The distribution of the zk's. So fill in the blanks. What's the mean? And the variance? What's that? Oh, this is great. You can't believe how it sounds back here. Well, it's t, but not t quite, because it's the distance traveled. So so it's the increment, the distance. That's right. So it's delta t times sigma squared. Right? Because basically you could translate this into a sum instead of an integral, and you get that. And anything else? And the most amazing property is this. I mean, it's not surprising at all if you look at a plot of this. I mean, if you go through, remember when we look at the original sum, it's discontinuous as hell, right? But then we're dividing by square root of n. So we're taking those increments and we're squishing them down by square root of n. So you wouldn't expect it to be discontinuous. But it's a horrible, horrible process. It functions, what's the probability that's differentiable at any point in time is 0. It's nowhere differentiable. So it's continuous, but it looks just like noise. I mean, it really, see, I can't draw it. You see, that's smooth. I mean, you can look at the slope there. It's got a beautiful difference. You can't draw it. It's completely fractal-like. If you zoomed in, it would look the same as you zoom out. And why is it nowhere differentiable? I can't prove that, but I can give you a hint. What would happen if I looked at 1 over delta times w of t plus delta minus w of t? That's the kind of thing you would look at if you want to differentiate, right? You'd take a particular t you're interested in, you'd look at the difference, divide by delta, and let delta go to 0. Now, I have no tools to study this, but at least I can look at its second moment, right? Because that's an increment, and that's something that I've just told you something about. So if I look at the variance, I'll need it, another bracket, I guess. The delta squared comes outside. And what's that? An increment of length delta, so that's equal to 1 over delta. Right. And so that goes to infinity. So the expectation of the second moment of the pre-derivative goes to infinity like delta. And the thing is that it's a bit confusing when you look at this. Where is it? Well, it's something like this. And so what you want to recall is that the variance of this increment so the variance is delta times sigma squared. You say, well, that's really small. But remember, the standard deviation is what you care about. And that's square root of delta. That's what's really easy to forget. And the square root of a small number, remember, that's a square root that has infinite derivative at 0. So that's what's killing us, is the fact that we get the standard deviation is square root of delta. That's all of it. Okay. So funny. I can't believe how ambitious I am. So this is again a huge building block. So how many of you think calculus is useful? I mean, stochastic calculus is really awesome and useful too. It's just that the reason is, and I didn't even take this, I didn't appreciate this until more recently. Just like you can calculate things with calculus, you've got all these beautiful tricks, integration by parts, and all these awesome things for computation. There's a stochastic calculus based on Brownian motion where you have all those tricks as well. So you can do all sorts of computations. How many think that discrete time, discrete time equivalents of calculus are useful? I mean, nobody. I mean, it's horrible when you look at discrete time calculations. Like the discrete time version of integration by parts is a nightmare. And discrete time is ugly, ugly, ugly for computation. So the reason we use these models, even though they don't there's no such thing as Brownian motion, is that they lead to computations really, really nicely. I mean, nobody has seen one of these guys. It does not exist. Nobody would say Brownian motion is a thing. It's a approximation of a random walk, which leads to really nice ways to calculate things. You know, that's the motivation. We're trying to come up with believe it or not, this is a simpler model of reality than the random walk thing we started with. Now, Symbiote communication will claim they have this is the noise in the communication channel, and have them see me. I'll suggest a psychiatrist. I don't believe it. I don't think anybody can claim that. You know, it's just no way. This doesn't exist. So, but sometimes it turns out to be a really good approximation for reality. And other times it's good enough. In a control problem, we want a simple model that captures features, and that is the simple model. I mean, this is a building block of it. So that would be the next topic, which would be stochastic differential equations. But this is when we stop. We do, no. But I can't get it. I can set it up. I can set it up and why it's hard. Yeah, but it's, I mean, yeah. Oh, what the hell? I'm definitely not going to go far. Don't worry. Nobody panic. Just to reassure you. Okay, but this is a challenge that we'd like to face. You know, so we're used to looking at x dot equals f of x, right? And what we'd really like to do is be able to introduce noise, and we'd like to introduce noise in such a way that we have a theory that's as beautiful as calculus is. I mean, people who use calculus learn to love it. So we'd like to put in a standard deviation term, and then white noise, you know, because given that this was constructed from a sequence of I, D, zero mean random variables, its derivative should be white noise, even though it doesn't exist. Right? And put this in quotation marks. Now, if you're a physicist, you most likely just write this, even though it doesn't exist. You know, I mean, if you look at a lot of physics papers that are published, they just write this. And they know they can make it justified, but it's so nice just to say it's an abstract, non-existent process. It's a process whose spectrum is completely uniform. You know, if you looked at its, if it did exist, its Fourier transform would be constant. You know, so it doesn't exist. But how would you make sense of this? If you're a control person, you wouldn't be so scared. All right? Any control people out there? You are. Any others? Why wouldn't a control person be scared? Because you're not really differentiating anything. There's a derivative on both sides. You're trying to solve a fixed point equation. So if you can be clever and rearrange this in some way, you know, you can get rid of the derivative. You know, I mean, x dot equals w dot's not scary. You would just say, well, xt equals wt plus plus x0 minus w0. The fact that you have derivatives on both sides makes you say, well, we can probably work this out. And it's been worked out. It's been worked out. Okay, so that's the point. You're not differentiating anything. So you have to write this in integral form. All right. So what you need to do is, next time, we need to make sense of something like this. So we want to do that if, anyway. And there's two ways of doing this. And one of them is the obvious way that you would have done based on learning about Riemann integration. You would approximate these integrals by sums, and that's approach number one. And there's another approach that's probably more valuable in terms of analytics, which I'll explain as well. But I'll talk about that a little bit next time. So basically, I'll make this precise as well as I can and talk about a few extensions, but we can't really get into this. I just want you to leave this course knowing what this is, knowing what this means. And I'm tempted to go further, but I can't. We'll do that next time. All right. So anyway, that's right, in office hours anyway. So this is a great place for office hours. So I'm not going to, nobody's coming in. So I'll just lecture's over. Have you turned it off? Yeah.